A black hole can destroy stars. It can tear planets apart. It can bend light, distort time, and hide an entire region of the universe behind a border no signal can cross. But here is the question almost no one asks. Can a black hole itself be destroyed? Not escaped, not avoided, destroyed. Could we attack it with energy? Could we throw antimatter into it? Could we spin it so fast that its horizon breaks? Could we somehow tear open the point of no return and expose whatever the black hole is hiding inside? At first, the idea sounds simple. Everything in the universe can be damaged. Stars die, galaxies collide, planets break apart, even atoms can be split. So surely a black hole, the darkest object in nature, must also have a weakness. But Einstein's universe is not that generous. A black hole is not a normal object with a surface you can crack. It is not a machine with parts. It is not a monster with skin. A black hole is a region of space-time where gravity has become so extreme that every possible path inward becomes easier than every possible path out. So if we want to destroy one, we first need to understand what we are really trying to destroy. To understand why this is so difficult, imagine standing outside the black hole with a perfect laboratory. You can measure it with impossible precision. You can watch matter fall toward it. You can track how it spins. You can read the way it bends nearby starlight. But you cannot open it and inspect its interior. Everything that crosses the horizon becomes part of a hidden history. This is unlike almost anything else in physics. If you burn a book, smoke, ash, and heat still carry information about what happened. If a star explodes, debris spreads through space and tells astronomers about the star that died. But a black hole hides the details. From outside, all the complicated history seems to collapse into a few numbers. This is why black holes feel so simple and so terrifying at the same time. A planet has mountains, oceans, storms, and chemistry. A star has layers, magnetic fields, fusion, and light. A living creature has structure. A black hole from the outside has almost no personality, mass, spin, charge. That is the public face it shows the universe. So any attempt to destroy it must fight not only gravity but simplicity. You cannot burn away features it no longer displays. You cannot poison a memory it no longer reveals. You cannot cut a surface it does not have. This also means that if we throw in a library, a mountain, a beam of radiation, or a cloud of antimatter, the outside description becomes brutally plain. The mass changes. The spin may change. The charge may change. But the stories are swallowed. Einstein's geometry turns biography into numbers, not the darkness, not the matter that fell in, the horizon. The event horizon is the invisible boundary around a black hole. Cross it, and the outside universe can no longer receive your light, your radio signal, or your final message. It is the point of no return, not because it is made of something hard, but because space-time itself no longer offers a road back. Einstein's theory tells us that gravity is not merely a force. Gravity is the bending of space-time. Around Earth, that bending is gentle. Around the sun, stronger. Around a black hole, it becomes so severe that light itself cannot escape once it passes the horizon. That means destroying a black hole is not like breaking a rock. It is like trying to break a rule of geometry. So let us begin with the most obvious idea: overwhelming force. Imagine bringing the most powerful weapons humanity can imagine and detonating them near a black hole. In ordinary life, explosions destroy things by pushing matter outward. A wall breaks, a building collapses, a planet's surface can be scarred. But a black hole does not work like ordinary matter. It does not have walls that can be blown apart. Energy that crosses the event horizon does not injure the black hole. It feeds it. This is where Einstein's famous equation becomes unavoidable. Energy and mass are connected. If you throw energy into a black hole, you increase the black hole's mass. If the mass increases, the event horizon grows. Instead of destroying it, The explosion makes the black hole slightly larger. The black hole does not care that the energy came from a weapon. It only cares that energy arrived. There is another way to see the problem. An explosion works by sending information outward. Pressure waves, fragments, heat, and light. But the event horizon is the region where outward information fails. Once the blast energy crosses the boundary, it cannot deliver destruction back outward through the horizon. It cannot tear open the prison from the inside. It simply becomes part of the prison's mass. In ordinary war, energy is damage. To a black hole, energy is dinner. So brute force fails. What about antimatter? Matter and antimatter annihilate when they meet, releasing energy. It sounds like the perfect cosmic poison. If you want to erase something made of matter, throw antimatter at it. But a black hole is not a normal ball of matter sitting behind a dark curtain. Once something crosses the event horizon, its past identity becomes almost irrelevant to the outside world. The black hole does not preserve the story of whether the object was a star, a planet, antimatter, radiation, or dust. From the outside, a black hole is described by only a few properties: mass, spin, and electric charge. The details of what fell in are hidden. This idea is often called the no-hair principle. A black hole has no visible hairstyle, no memory you can read from outside, no label saying what created it. So if you throw antimatter into a black hole, the result is not cancellation. It is more mass energy. The black hole grows again. Now the game changes. If adding energy makes the black hole bigger, perhaps we need to attack not its mass, but its identity. A black hole can spin. A black hole can carry electric charge. And in the mathematics of general relativity, there are limits. A black hole cannot spin arbitrarily fast. It cannot hold arbitrary charge. If it somehow exceeded those limits, the event horizon could, in theory, disappear. And if the event horizon disappears, the black hole is no longer a black hole in the usual sense. The prison door would be gone. Think of the horizon as a line not drawn in space, but drawn in the future. Outside the line, there are futures where a signal escapes and futures where it falls in. Inside the line, the escape futures are gone. You can still move. You can still fire rockets. You can still choose directions locally, but none of those choices lead to the outside universe. That is why removing the horizon is such a dangerous idea. It would not simply turn the black hole into a dead star. It would expose the failure point of space-time, the place where the mathematics of general relativity says curvature has become infinite. What remains would be far more disturbing, a naked singularity. In the simple picture, the singularity is the place where Einstein's equations predict curvature becomes infinite. But we must be careful. The singularity is not a photographed object. It is not a confirmed physical bead at the center. It is a sign that our theory has reached an extreme point where the mathematics stops giving ordinary answers. Normally, the event horizon hides this failure from the rest of the universe. That may be more important than it sounds. Inside a black hole, the singularity is not simply a place ahead in the ordinary sense. After crossing the horizon, it lies in your future. Reaching it is not like walking toward a wall. It is more like moving toward tomorrow. You cannot turn away from it for the same reason you cannot turn away from the next second of your life. This is the terrifying geometry Einstein's theory allows. The event horizon seals that future away from everyone outside. Whatever happens where the equations fail cannot send messages back to the universe. The madness is hidden behind a cosmic curtain. But if we destroyed the horizon, that curtain would be removed. The singularity would be exposed. This is not just a poetic fear. Modern physics is built on predictability. We write equations because the universe normally gives us rules. If we know the present accurately enough, the laws of physics tell us what can happen next. A naked singularity threatens that confidence. It is not merely an unknown object. It is a place where the stage on which objects exist may no longer behave like a stage at all. That is why the question, can we destroy a black hole, quietly becomes, can we expose the place where physics breaks? And that is a much more dangerous question. A naked singularity would be a place where predictability may break down in view of the universe. Physics depends on the idea that causes led to effects in a lawful way. If space-time itself fails in an exposed region, then our ability to predict what happens next may collapse. Not because we lack better instruments, but because the rules we use to define where and when no longer behave normally. This is why many physicists suspect nature protects the universe through something called cosmic censorship. The idea is not fully proven in every possible case, but it suggests that singularities formed by collapse should remain hidden behind event horizons. The universe may prevent naked singularities from appearing, not out of kindness, but because without horizons, physics itself could lose meaning. So perhaps the event horizon is not the villain. Perhaps the horizon is the shield. The thing that traps you may also be the thing that protects the rest of reality from whatever lies beyond known science. Still, suppose we try. Could we overcharge a black hole? Imagine throwing more and more charged particles into it, trying to push its electric charge beyond the allowed limit. At first, the charge increases, but as it grows, the black hole repels particles with the same charge more strongly. The closer it gets to the limit, the harder it becomes to add more. The black hole resists being pushed over the edge. Could we overspin it instead? We might throw matter in at just the right angle, adding angular momentum faster than mass. A spinning black hole drags space-time around it, and near the extreme limit, the mathematics becomes delicate. Some calculations suggest possible loopholes. Maybe, in a carefully arranged scenario, you could feed the black hole just the right amount of spin at just the right moment. But nature is not a quiet chalkboard. Real black holes are surrounded by radiation, fields, particles, and disturbances. The very matter you throw in changes the space-time around it. Effects ignored in simple calculations may save the horizon at the last moment. Many physicists expect that attempts to overspin or overcharge a real black hole would fail before the horizon disappears. The black hole would adjust. The excess would be rejected, or the added mass would keep the horizon intact. This is why black holes are strange opponents. They do not fight back like living creatures. They do not need armor. Their defense is written into the structure of space-time. The closer you push them to a forbidden state, the more the surrounding physics seems to arrange itself against your plan. The exact mathematics is complicated, and physicists still argue about extreme theoretical cases. But for a real object in a real universe, with radiation, gravity, charge, and back reaction all present, the event horizon appears remarkably hard to remove. This is the pattern again and again. The black hole turns attacks into food. Energy makes it heavier. Antimatter makes it heavier. Collisions make it larger. Attempts to push its spin or charge may be blocked by the same physics that defines it. What if we use another black hole? If two black holes collide, do they destroy each other? No, they merge. For a short moment, space-time shakes so violently that gravitational waves ripple outward across the universe. These waves carry away energy. Detectors on Earth have measured such ripples from black hole mergers, but after the collision, the result is not nothing. It is a larger black hole with a new mass and spin ringing down into a stable form. Even black holes cannot kill black holes by collision. They create bigger black holes. This is why the word destroy becomes slippery. You can change a black hole, you can make it grow, you can merge it, you can drain rotational energy from it in certain processes, you may be able to reduce its spin. But removing the horizon completely in a violent attack appears far harder than science fiction suggests. There is, however, one method that does not require weapons. Wait. Stephen Hawking showed that black holes are not perfectly silent when quantum physics is considered near the horizon. They should emit an incredibly faint form of radiation, now called Hawking radiation. This means black holes can slowly lose mass. If nothing feeds them, they shrink over enormous timescales. For stellar and supermassive black holes, this process is almost unimaginably slow. A black hole with the mass of the Sun would take far longer than the current age of the universe to evaporate. A supermassive black hole would survive on timescales so vast that ordinary cosmic history seems brief by comparison. And even Hawking radiation should be understood carefully. It is not ordinary light escaping from inside the black hole. Nothing inside the horizon sends a message out. The radiation is a quantum effect associated with the horizon and the curved space-time around it. From far away, the result is that the black hole loses energy and therefore mass. The horizon shrinks. For large black holes, the effect is so tiny that the cosmic microwave background and surrounding matter can feed them more than they lose today. Only in an unimaginably far future, when the universe has cooled and emptied, would large black holes truly begin their long decline, but the principle matters. A black hole can die, not by explosion from outside, not by antimatter, not by being smashed, but by slowly leaking away through quantum effects at its horizon. At the end of this process, if our theories are correct, the black hole evaporates. The event horizon disappears. What exactly happens in the final instant is still one of the deep questions of physics, because that tiny final stage requires both gravity and quantum mechanics working together. We do not yet have a complete theory of quantum gravity. So even the safest method ends at a mystery. This is the strange lesson. The only reliable way to destroy a black hole may be to let the universe do it slowly, across timescales beyond imagination. Einstein gave us the geometry. Hawking added the quantum whisper. Together, they turned black holes from eternal prisons into objects with a beginning, a life, and perhaps an end. But the end is not something a civilization can easily force. The horizon is too good at turning violence into growth, and maybe that is the deeper reason black holes matter. They are not just cosmic monsters. They are tests of the rules. If we try to break them open, we risk exposing the place where our theories fail. If we feed them, they grow. If we collide them, they merge. If we wait long enough, they fade. A black hole is both a prison and a protector. It imprisons everything that crosses its horizon, but it may also protect the universe from the naked chaos of a singularity. That changes the way we see it. The darkness is not merely destruction, it is censorship, a silence placed around the point where physics loses its language. So can a black hole be destroyed? Yes, but not like a planet, not like a star, and not like an enemy. You cannot blow it apart. You cannot poison it with antimatter. You probably cannot tear away its horizon without challenging the structure of physics itself. The one method we trust is patience on a scale almost beyond meaning, Hawking radiation slowly reducing the black hole until, after an unimaginable future, the horizon disappears. And perhaps by then, the universe itself will be old, cold, and nearly empty. No stars, no galaxies shining as they do now. Only fading remnants, silent particles, and black holes slowly whispering themselves away. In the end, the most powerful objects in the universe may not die with a roar. They may die by becoming almost nothing. That is the final irony Einstein never lived to see fully. The object from which nothing can escape may spend eternity escaping from itself. A black hole can destroy stars, but time may destroy the black hole. What feels more terrifying? A universe where black holes live forever, or a universe so old that even black holes finally disappear? Subscribe to explore more documentaries through Einstein's questions, the questions that still lead us to the edge of reality.